Okay, the input is different from the what we always using, which is a sine wave, but doesn't matter at all because this is even easier than the sine wave. The sine wave, is a continuous, it's a curvy, but this is even easier. And the principles are the same, exactly the same. Okay, here, as I will show you now, we will solve it just exactly the same way we did with the sine wave and the circuits that we see maybe 3 or 4 lectures ago. Okay, so let's see what's gonna happen in here, like is a half wave rectifier, I mean. So initially the capacitor has no charge initially. As we always assume, okay? So Q is equal to 0. Q is the capacitor charge at T equal to 0. Here. Okay, and we know that Q is equal to CV. C is constant, the capacitance of the capacitor. So VC, which is equal to VO, is equal to 0 at T equal to 0. Okay, so if this is ground, this will be 0 as well. The voltage will be 0. And here we have a battery of 5 volt. Okay, so the voltage of that point here is 5 volt. This is at T equal to 0. Okay, so for this diode here to conduct, to be on, we know that it should have 0.7 volt. So that point should be greater than in voltage than this point by 0.7. Okay, so this should at least have 5.7 so that the diode can conduct. So let's call it V1, for example, something like this. So in order for the diode to be on, V1 must be equal to or larger than or equal to 5.7. So when the input is less than 5.7, the diode is off. So the current is equal to 0. This is the current, which is equal to the current of the capacitor. So there is no current flowing in the capacitor. So the capacitor will not charge. So as long as V input is less than 5.7, VC is equal to 0 because there is no charge on the capacitor plates, which is equal to VO. So let's do that. So let's assume this is 5.7, so this is 5, this is 5.7. Okay, as long as V input is less than 5.7, the capacitor has a 0 volt. And all these values here are less than 5.7. So the capacitor output will be 0. Okay. Now, when the input exceeds 5.7, these values here are more than 5.7. So the diode will be on. So ID, which is equal to IC, because they are in series, will be larger than or equal to 0. That means the capacitor will charge. There will be charges on the capacitor plates. So its voltage will rise up. Okay? So it will just follow the input at that point. And we can do that. We can prove it analytically. So VC with these conditions here, okay, is equal to V input minus 0.7 because the diode is on, minus 5. This is by Kirchhoff. This is VC, this is the 5, this is the 0.7, and this is V input. So by Kirchhoff, V input is equal to all the voltages, equal to VC plus 0.7 plus 5. So VC is equal to V input minus 5 minus 0.7. So what I did here, I take each point here and subtract 5.7. At that point, V input is 5.7. So 5.7 minus 5.7 will give you 0. At that point, V input is equal to 10. 10 minus 5.7 is equal to 4.3 volt. This is exactly what we have done with the sine wave. Nothing new here. And when we continue now, we will discover that also nothing new. Now, after this point, which is t over 2, because the period here is from this point to this point, let's call it t. What's happened after t over 2? Exactly like what happened when there is a sine wave. After this point, the input is wanna decrease, is decreasing. So the capacitor wanna discharge. For the capacitor to discharge, it should charge in that way. So the capacitor, when it was charging, the current was flowing in that way. So this was the positive, this was the negative. When the capacitor tried to discharge, it discharged in an opposite direction to the charging current. So the discharging current will be in that way. That way. And in order to do that, this is not gonna happen because the diode cannot permit current flowing in that way from N to P. So that, let's write this down here. Okay. For t larger than t over 2, for any time greater than t over 2, forever until infinity, the diode or the capacitor cannot discharge its charges or whatever. It's, yeah, cannot discharge, and that's it. Because the diode does not allow positive current to flow from N, its N to its P in that way. This is not gonna happen. And if you remember, if you go back, we said that after another explanation for it, after t over 2, whatever the value of V input, even at the maximum value, the diode will be off. So another explanation for that, you can go with this or you can go with this, they are both the same. After also t larger than T over 2, the diode is off all the time. All the time the diode will be off, from here to infinity. So if the capacitor now cannot discharge, it will keep its voltage, because the charge that it has on its plate doesn't decrease or increase. So the voltage will be the same all the time. So based on that, VC, which is VO, equal to 4.3 voltage forever. So if we go back here and continue drawing this, and if you go back to the lecture, the half-of lecture with the smoothing capacitor, I picked some values for V input. I proved that with these values, that the diode was off. Okay, so this is the correct answer for this question. Okay. Any question about this? So some argue that we didn't take, homeworks or some training, you can say, with triangular wave. Yes, I didn't do that because you have the harder, so this is the easier. Okay, but I appreciate, of course, the answer. That's very fine. I accept it. Okay. Yeah, it has some logic, because, and the most important logic in this answer of the survey is that there is no negative. But again, if there is no negative, we didn't refer to the positive or negative side when we take the sine wave, because we said that after it was T over 4 at that time. Okay, the diode will be off all the time. So if the diode was off for negative, for some of the positive, it will be also off or reverse with the negative inputs. Okay. So that was the answer for question 17. And again, don't worry about the marks. It's gonna be fixed. Okay. Let's go to question 16. This is a very nice one. Okay. We have, so just sketch VO versus V input. Luckily, many of you has done this right, but some didn't. But let's see. So this is diode 1 or Zener 1. This is diode 2 or Zener 2, whatever you call it. So V breakdown 2 is 10. So this guy here has a V breakdown equal to 10. Let's call it 2. And the first one has a V breakdown 6.3. Okay. And in forward, when they conduct in forward bias, they both have 0.7 volt. And just a sketch VO versus V input. And here is the input. The input is square wave. Which is even easier than the triangular and the sine wave. Okay. I will draw both at the same time on the same graph. It will be easier to understand. So this is 20 and this is minus 20. So let's first, when the input or the positive half cycle, when the input is equal to 20, the positive half cycle. You can, because it's a square wave, you can draw the circuit like this, just with a battery equal to 20, because it's constant. You can draw it like this. Okay, this is diode 1, this is diode 2. Now, to solve it, we need to know which is forward and which is reverse. D1 is reverse. D2 is forward. Okay. The zener, if we draw its characteristic, it would be something like this. 0.7 in forward to conduct, and VBD in reverse to conduct. That means for forward to conduct, the input must be larger than or equal to some value, probably larger than 0.7. So the diode can conduct in forward. And in reverse, the reverse voltage should be in magnitude larger than V breakdown in order to make the zener conduct. Let's see. We have here one source for both, for D1 and D2. One of them is forward, so it needs only 0.7. And this guy is 20. And the other guy in reverse, D1, and it needs V breakdown 1 is 6.3. And again, we have 20. So this guy needs 0.7. And this guy needs, in that direction, minus 6.3, or in that direction, 6.3. The total of both is 7. And 7 is much, much less than 20, right? So it's here, it's good to assume that both are on. One of them on in forward and the other is on in reverse. So D1 on but in breakdown, and D2 is on but in forward. And we're gonna prove it's correct by just calculating the current. And here is VO. VO is simply 0.7 plus 6.3. Which is 7 volt. Now let's prove it's correct. So we know if we have a diode on in forward, its current should be positive, larger than 0 and positive, of course. And if we have a diode or zener conducting in reverse in breakdown, its current should be larger than, as the magnitude larger than 0 and negative. So let's see that. So this is ID1. Oh, I'm sorry, ID2. And this is ID1. If you notice, they are in opposite directions. So, but they are in series. So ID1 equal to minus ID2. Okay, what is let's calculate this current here. This current here, which is equal to ID2 because it's the same direction. ID2 equal to this point, which is 20, minus this point, which is VO, over 100 ohms. 20 minus, what's VO? It's 7 over 100, 13 over 100, which is 13 amps, which is positive. So ID2 is positive. ID2 is forward, and for forward, we need the current to be positive. And the ID1 is equal to minus ID2. So it's equal minus 0.30 amps. And we want ID2 to be negative. It should be negative. So the assumption is correct. And the VO is 7 volt. So if we draw VO here, this is maybe 10. So this is 7, for example. Now number 2, when V input equal to minus 20, or the negative half cycle. So this is, since it's a square wave and the voltage is constant in negative half cycle, you can just replace it with a battery with a constant voltage. And again, we have D1 original 1 and D2 original 2. Okay, let's do it with another color. Okay, you can flip this battery to make it easier for you. And make it 20, since you flipped the polarity, because the direction was in that way, now the direction is that way. When you flip the direction, you should flip the polarity. This is Mr. D1, this is Mr. D2. D2 is forward. Just look at it. N is close to the B, and B is close to the positive, I'm sorry. Yeah. And D2 is reverse, just the opposite of the first cycle, negative half cycle, or positive half cycle. The B is close to the N, and I'm sorry, the negative, and the N is close to the positive. That's why it's reverse. This guy to conduct in forward, it needs 0.7 in that way. And this guy to conduct in reverse, it needs minus 10. Yes, minus 10. Yes, minus 10 in that way. Or 10 in that way. If you notice, both has, going downward like the input. And again here, both, this guy and this guy, are upward like the input. So total we need 10.7. And the input is 20. So probably they are on. So both assume, we prove that's correct, on. For D1, it's on in forward. For D2, it's on in breakdown. And again, we're gonna prove if we are right or wrong based on the current. So D1 is forward, so the current that flows in that direction, ID1, should be positive. And D2, with the current flowing in that direction, should be negative. Again, for a diode to conduct in reverse, the current should be negative. And here is VO. Now VO, if you notice, VO is upward and these two guys are downward. So VO is minus 10.7, or minus 10 minus 0.7 equal to minus 10.7. So let's calculate ID1. ID1 equal to this point minus this point over 100 ohm. This point is VO. And this point, this is the ground. And this is larger than this by 20. So this is minus 20 over 100. VO is minus 10.7. Minus and minus will be plus 20 over 100. So this is equal to 9.3 over 100. 93 amps. It's positive. And we want ID1 to be positive because it's forward. And I, D2 is minus ID1. So it's equal to minus It's negative. And that's right, it should be negative because it's conducting but in reverse, in breakdown. So that assumption is correct, and VO is correct, equal to minus 10.7. Let's draw it. So a negative half cycle minus, let's say this is minus 10.7. And what's happened in the first cycle will happen also in the second cycle. And so on. I don't know, Sturgis. What do you mean? You got 16. I don't know. What do you mean? Okay, guys, this is clear. You have a question on that? I don't know. We're gonna see. Okay, so let's do another one. So let's see another question. Yeah, let's go now to the question. It's not, it's related to the, not question 16, but we're gonna deal with this circuit here, this one. There was a lot of question about this circuit. This circuit was in the homework, but it was ideal diode. Okay, so the only change now, is that this is not an ideal diode. This guy, when it conducts, it needs 0.7. I'm saying using the constant voltage model. So that's the only difference from the homework. Of course, plus some questions, some other questions. Okay, this guy called the VB, this guy called the VX. Okay, R1, R2, and here is I2, here is I1, here is something called IX. Okay, good. So I am not gonna solve all the questions, but I wanna highlight 3 main questions of them, maybe to show you the best way to deal with such circuit. The best way to deal with it is to find the input minimum that will turn the diode on, but in terms of the circuit parameters like R1 and VB, R1, R2, and VB. And to find the VB that will turn the diode off. And let's see, this is maybe something new, because we always say the input minimum that will turn the diode on. But this if the input is connected as forward to the diode. But VB here is connected reverse. So VX, so this is, let's start. What question is that? So this should be, yeah, question 8. Eight, 9, and I also will solve maybe the last one. 15. Yeah, I will solve this 3. Okay. So let's see. So Vx is connected forward to the diode. Just look at it. The positive is with B, the negative is with N. Sorry, the positive is with B, the negative is with N. Or you can do it in another way. Just look at the current that the battery wanna push into the diode and check the directions. Okay, so this battery wanna make the current like this. You see. So the current that this battery wanna push into the diode is flowing from B to N. So that battery has a tendency to turn the diode on or forward. It's connected forward. The other one, VB is connected reverse. Let's see that. So the negative is close to the B, the positive is close to the N. In another word, if we just assume that there is no source here, okay, just assume this. Let's do it another color. So this is the current that goes out of the battery, VB. It will be divided here to this branch and to this branch. And look now how it's flowing in the diode. It's flowing from N to B. And of course, that's not gonna happen. Okay. So VB is connected reverse. To the diode. Okay. So Vx minimum is actually the minimum input voltage for Vx that will turn the diode on. But VB minimum is something opposite. It will turn the diode off. Okay. So we can imagine it or visualize it in using this very simple diagram. So let's do with here. If this is Vx, for example, and here is, for example, Vx minimum. Beyond that point, the diode is on. And below this point, or less than Vx minimum, the diode is off. But for VB, it's different. It's opposite, not the different. If this is VB, if this is VB minimum, here the diode is off. Here the diode is on. I mean, we need to decrease VB in order to make the diode to be on, because it's reverse. And we need to increase Vx in order to turn the diode on, because it's forward. Okay? So let's do that. So let's do 8, and in 8, it was asking about Vx minimum to turn the diode on. So at Vx minimum, the diode is just on. That means Vd is equal to 0.7, but Id is equal to 0. And my advice here is to do it using the circuit parameters, without just substitute at the end. Good. So let's see what we have. Since ID is 0, we have here at that node I1 equal to ID plus I2. ID is 0, so this is equal to I2. Good. So what's I1? I1 is flowing in that direction in R1. So it can be equal to this guy, this voltage minus this voltage over R1. So what is this? If this is the ground, this should be Vx. Vx minimum in that case. And if this is the ground, we know this is greater than this by 0.7. So this will be 0.7. Good. So I1 is equal to Vx minimum minus 0.7 over R1. equal to I2. What's I2? And now look, I2 is flowing in upward from that point, you know, that point. So it's equal to that point minus this point over R2. So what is the voltage of that point? We have here 0.7 and we have here a battery of VB. So that means this is greater than this by VB. So this should be VB plus 0.7 because the voltage difference should be VB. VB plus 0.7 minus 0.7 will be VB. Good. So this point VB plus 0.7 minus this point, which is Vx minimum, over R2. And just to continue in simplification of this, the left and right hand side, you will get at the end Vx minimum equal to 0.7 plus VB multiplied by or times 1 plus R2 over R1. That will make your life very easy in the rest of the questions. Because now you see what's gonna affect Vx minimum. What if R1 is short, or R2 is open or short, or R1, you know, you can substitute whatever in this equation and you would know what's gonna happen to Vx minimum. For example, if there is no VB, if there is no battery here, we just need 0.7. If VB is 0, we just need 0.7. But because VB is reverse, it's affecting Vx minimum. Because Vx minimum, in order to turn the light on, should, you know, reflect the effect of VB, which is reverse, and also provide the 0.7. Okay. Now let's do. Now, of course, you can now substitute if R1 equal to R2 equal to 1 and the VB is equal to 1. This would be, let's say, equal to 0.7 plus 1 multiplied by 1 over 1 plus 1, which is 0.7 plus half, which is 1.2 volt. Okay. Now, number 9, VB minimum. That will turn the diode off. And let's here go and draw or plot the characteristics. This is VD, this is ID. This point here is off, here is on. So at VB minimum, the diode is just off again. So it's also working in that point. This is just on or just off because it's in between. Okay, so at VB minimum, the diode is just off on the edge. So VD is still 0.7 and ID is 0. If ID is 0, then I1 equal to I2 and ID is 0 because ID is 0. And if I1 equal to I2, then we can do that again. But now it's Vx minus 0.7 over R1 equal to VB minimum plus 0.7 minus Vx because now our parameter are the things that we, Vx now is a parameter and the thing that we want to determine is VB minimum over R2. And we will just, you know, reach to something like this, but, you know, VB in the left hand side and Vx on the right hand side. So based on that, VB would be VB minimum equal to, where is the equation here? 1 plus R2 over R1 Vx minus 0.7. Okay. Now let's state these facts. So that is, of course, if you wanna, at R1 equal to R2 equal to 1 and Vx equal to 1, let's do that. 1 plus 1 over 1 and 1 minus 0.7. So this will be 2 multiplied by 0.3. It's 0.6. Okay. Now some facts here. If VB is larger than VB minimum, the diode is sure of, not on. That's the opposite to Vx minimum. And if VB is less than VB minimum, the diode is on. Opposite to Vx. If Vx is larger than Vx minimum, the diode is on. If Vx less than Vx minimum, the diode is off. And the beauty of having the equation like this again, you can determine what will affect VB minimum. If R2 is open, if R2 is short, if there is no Vx, all such stuff. If there is no Vx, by the way, then VB minimum is negative actually. Would be negative. Okay. Good. So based on these two equations, now we can solve other questions as well. Okay. Now the last question, which is related to this circuit, which is 15. So let's do 15 now. If 15, it says that, let's have it here. If Vx equal to VB and Vx is larger than 1.4 and R1 equal to R2, the diode is on. And true or false? This is true or false? Let's see. This is a circuit. Let's even draw it, with battery symbols. So Vx is equal to VB, call it E. So E, whatever, because they are equal. So call them with the same, same symbol. And again, R1 equal to R2, so call them R. So R and R. Okay, if the diode is on, that means ID is greater than or equal to 0. Or greater than 0. This point at ID equal to 0 and VD is 0.7, it's in between. It's a transition point. But anyways, you can consider it on or off. That doesn't matter. And of course, VD is equal to 0.7. Okay. This is I1, and this is I2, and this is ID, or IX. So I1 equal to I2 plus ID. That means ID is larger, equal to I1 minus I2. If the diode is on, that means this should be larger than or equal to 0. Okay, what's I1? I1 is equal to this point minus this point over R. This point is E, and this point is 0.7 over R minus. I2 is flowing in that direction. It's equal to that point minus this point over R. That point here is E plus 0.7. E plus 0.7. And that point is E over R. That should be larger than or equal to 0. Okay. This will go with this. And you can multiply by R. So this will be reduced to E minus 0.7 minus plus minus 0.7 again, because minus will go there, so it will convert this to minus again. Minus 0.7 larger than or equal to 0. So E should be larger than 1.4 if the tide is on. And the question says that Vx, which is E, is larger than 1.4. That's why the tide is on. So it's really correct. It's a correct statement. Okay? This is clear? Any question? So now, guys, I will share the other screen with you, and we will, browse the questions together. And if another question you want to solve, let me know. So you can see my other screen.
I can see it.
Good. So anyone has a trouble with question 1? Question 2?
Could we do any of the doping questions?
Okay. So you mean a question including question 1 and question 2, or the other questions also? Okay, let's do 2. So 1 is very easy. So this is 300 degree Kelvin. So this will be approximately equal to ND. So Bn will be equal to Nd over Ni square. So Nd is 10 to the power 6. I'm sorry, the opposite. Ni square over Nd. So 10 to the power 20, because it's a square, over 10 to the power 16, it will be 10 to the power 4. So the answer should be B. Here, the temperature changes. If you remember, guys, I did this example with you, but I just changed the number. So we did something very similar, but with T equal to 800. I just changed the temperature. Nothing new here. So let's do this is question 2. So T is equal to 1000 Kelvin. Okay? 1000 Kelvin. So Ni will change. And you have the formula for Ni. It's 5.2 10 to the power 15 T to the power 3 over 2.
You want to swap screens if you want to show them work?
Oh, yeah. Thank you. Thank you. Okay. You see it now?
Yeah, they can see it.
Minus Eg over Kt over Q. And this Q, since it's the denominator of the denominator, so it can be go up here in the numerator. Okay, like the formula that I published in the cheat sheet. So this guy here is 1.12. K is given, Boltzmann constant. This is 1000. And Q is 1.66, 10 to the power minus 19. Okay. Then you calculate that. So Ni would be what? Yes. Ni would be 2497 10 to the power 17. Okay? This is a new Ni. Then
Is there supposed to be a 2 in the exponent for the bottom of the division part?
in the NI equation.
Yeah.
So let's go to the cheat sheet and see. Yeah, I'm sorry. There is 2. So you have the cheat sheet. You know, it's. I'm just try to remember it with you. But if you do that, if you compensate here, you will get this number 2.497 10 to the power 17. Okay. Now with that now we know that Pn equal to Ni squared. Okay. And we know from the what do you call it, charge equality, that the positive charge should be equal to the negative charge, like what we said, like what we said at that time, that the negative charge equal to the positive charges. If you have a sample of silicon like this, and it's doped by phosphorus, there will be N electrons, negative charge. There will be holes, which are positive charge, and there will be another positive ions, which is positive charge, which is the Nd itself. So N equal to, or Nn equal to Pn, which is the holes, plus Nd, which is the dopant atoms. Okay, and from that equation here, you can say that Nn equal to Ni square over Bn. So you can compensate with that equation here. Okay, then you will get that Bn square plus Nd Bn minus Ni square equal to 0. Then you solve this, Bn equal to minus Nd over 2 plus or minus Nd square over 4 plus 4 Ni square over 4. Okay, you exclude the minus, because if you include the minus, you will have a concentration in minus, which is not correct. You will go only with the positive. So based on that, Bn equal to 2.448 10 to the power 17 again. And based on that, if you go back to this equation here, we can get Nn. Nn would be, something Ni squared 10 to 2497 10 to the power 17 square over 2448 10 to the power 17. It will be something, I don't have the number here, but it will be something very, very close to that one. Slightly larger than this one. Slightly larger than. Okay. So you will find that Nn approximately equal to Pn. That's why this sample is intrinsic, which is question 3. Question 3 is dependent on question 2. So if you calculate Nn, you will find it very close to Pn. That means the positive holes, or the positive carrier charges approximately equal to the negative carrier charges. That's why we can consider this piece of silicon as intrinsic piece of silicon, although it's doped by phosphorus. But because of the temperature, both become approximately equal. Okay. Let's do question 4, because it's good also. So in question 4, so any p-n junction should have n part and p part, p-type part, okay? So it says that due to some manufacturing error, the p side of the p-n junction hasn't been doped. So no doping here. In the p side. But still here, in the inside, we have ND. So what is the built-in potential voltage? Basically, VB I equal to VT ln NA ND over NI squared. If there is no doping here, that doesn't mean NA is equal to 0. That means that the doping here is that Bn equal to Np, equal of course to Ni. So that portion here will be reduced to Ni. So that will be Vt ln Ni Nd over Ni square. So this will go the square. So Vt ln Nd over Ni. If you calculate this, this will be 0.359 volt, because this is a voltage. Okay. So basically, that equation is that says the following: take the concentration on the majority concentration on N side. This is the majority concentration on B side. So on the B side, there is no the majority on the N side is ND. The concentration of the majority on the B side, although it's equal, there is no majority. You can take any. So we take Ni, because any is equal to Ni. Bn, I'm sorry, PP. This is BB. I'm sorry, this is BB. BB equal to NB equal to Ni, because there was no doping, because of this errors that happens during the manufacturing process. Okay, and this is actually a question in the book, and I told you to solve, look at the questions there. What else we have? Yeah, there is also a very good question. So let's do that, which is question 7. So in question 7, we have a circuit like this. So two identical diodes in parallel with a resistor. Then we have a constant current source. Constant current. So this is also a question in the book. Okay. Here is R, which is unknown. Here is D1, here is D2. So D1 and D2 are identical. Okay, I will do that. I will do the capacitor. Okay. So let's finish this. This is easy also. So D1 equal to D2. I'm sorry, identical to D2. So two diodes that are identical, and that means if you have the characteristics like this, and you know the current, then you know the voltage. Good. Both currents are the same. ID1 equal to ID2. Let's call it ID, because they are in series. So if you know this current, okay, just if you know the characteristics, the equation and stuff, if you determine this current, then you go back, this is VD. So both will be the same, because they have the same characteristics, because they are identical. since they are identical, and ID1 equal to ID2, and they have the same current, identical and have the same current, then they have the same voltage. VD1 equal to VD2. Let's call it VD. So here is VD, here is VD. And let's call both currents ID. Okay. Another given in the example is that I, here, there is a current called I equal to 0.5 milliamperes. And the current here, the current source actually is 1 milliamperes. It's called IX. So here is IX. IX equal to I plus ID. This is 1 milliamperes. This is 0.5 milliamperes. And ID is unknown. So ID is equal to 0.5 milliamperes. The last given, it forces you to use, you know, the accurate model, the equation, that ID equal to IS exponential VD over VT. For any diode, this is, and IS equal to 5 to the 10 minus 16 amperes. Good. So ID equal to IS exponential VD over VT. Okay, that's I. And VR, the voltage across the capacitor, I'm sorry, the resistor, this is this guy, VR, is equal to IR. Okay. At the same time, the resistor is in parallel with these two diodes. If we make a loop here with Kirchhoff voltage law, you will find that VR equal to VD plus VD, which is equal to 2VD. So by Kirchhoff, this is equal to 2VD. So R equal to 2 divided by R multiplied by VD. So let's get VD from here. So you can divide by IS, so, and then take the len to the both sides. So VD is equal to VT len ID over IS. And do you know ID is equal to 0.5 milliamperes? This guy is 5 to the 10 to the power minus 16 amperes. So you should convert this to amperes or convert this to milliamperes. And VT is 26 millivolt or 0.026 volts. Then you can determine VD. If you do this, VD is 0.7184. Okay, so go back to the equation here. 2 and the I is 0.5 milliamperes. You should convert it or keep it, whatever, multiplied by 0.7184. If you convert this to amperes, you know, and you make the multiplications and stuff, this would be 2073.62 ohms. Any question on that? So let's do very quick the capacitor, which is the varactor diode stuff. Yeah, you have here, so this is question 5. So you know CJ0, if you have a varactor like this, varactor diode like this. This B is N. So we said that this is like a capacitor. This is, you know, one of the plates is another plate, and you have here, you know, insulator. This is just a capacitor. Okay. CG0 is equal to the square root of what? I forgot. Epsilon Q over 2. Let's go to the cheat sheet. Yeah. NA, ND, NA plus ND, and 1 over VBR. Okay. In the question, it gave you NA and ND. So the phosphorus, which is ND, equal to 9, 10 to the power 15 per centimeter cube, or centimeter minus 3. And the boron, which is Na, acceptors, 2 to the 10 to the power 16. Okay. But doesn't give you VBI. So you should determine VBI first. So VBI, this is step 1. VBI, VT, len, Na, Nd over Ni square. If you calculate that guy, where it is? Point 733 volt. Good. And you have NA. Now epsilon. Epsilon is called second step. Epsilon is epsilon R multiplied by epsilon naught, 11.7 multiplied by 8.85, 10 to the power minus 12. This is farad per meter square. So look for take care here because this is centimeter and this is meters. So you should convert one of them to the other. Okay. Now everything is known. We have VBI, we have Na and Nd, we have epsilon, so we can determine CG0. But remember something here that I mentioned in our lecture. Let's see, this is in farad per meter square. I mean, it's per unit area. If everything here is in centimeters, this will be farad per centimeter square. If everything here is in meters, so this will be farad per meter square. Okay? So you should convert one of them to the other. Whatever, that's completely for you. So if you do that, you will find that CG0 equal to 2648 10 to the power minus 4 farad meter square. I think this is also a solved example in the book with the same numbers. I think so. Yeah. This is actually an example in the book, and it was a homework, by the way, with the same numbers. I didn't change them. Now, the capacitance in farad without this meter square, we should multiply this by the area, and the area is given as 2000 micrometer square. So here area is known.
I'm sorry. Which example in the book is this?
Yeah, the one that was in the homework, but I just didn't complete it. I mean, I didn't ask you for the frequency. So example 215. Page
Thank you.
43. Okay, so it's a big example there because it asks. There are many, many other questions. Like for example, it determines resonance frequency and stuff, like the homework. But I just clipped it at some point, which is finding the capacitance. So yeah, you just take this value here, 2648, and be careful with the dimensions, because this is meter square, this is micrometer square. So what it asks for, it's asks for femtofarad. So let's do it in farad first, then we convert to femto, 2000, and micrometer square means 10 to the power minus, if you convert it to meter square, it will be 10 to the power minus 12. Okay, micro is 10 to the power minus 6, and you have here micrometer square, so 10 to the power minus 12. Okay, and to convert to from farad to femtofarad, you should multiply by 10 to the power 15. So again, 10 to the power 15. So this is the conversion, and this is the area, and this is this value here. Okay, if you do that, it will be to 65 femto. Oh no, it will be what? No, not this one. It will be 529. Yeah. 529.6 femtofarads. Okay.